Okay, everybody, it's a big day today. It's the last one. This is the end. If you've made it this far, you've done it. You made it through linear algebra. Hopefully this was a good class. Hopefully you learned a lot. It's been a genuine pleasure having each and every one of you as my students, and it's been a lot of fun. It's been a lot of fun to read your work and watch you grow as mathematicians, and everybody who took this class, I very confidently can say, improved extremely substantially in their ability to write proofs. We wrote many. You wrote hundreds of them with me over the course of this semester, and I hope you got something out of it. I hope you have a deeper appreciation and understanding of linear algebra, and I hope it's been a good experience. It's probably been kind of hard, but after all good math classes are. So I'm not saying this one's necessarily a good one, but I hope you think it was. At least I'm trying to make it a good one. So let's end the class by bringing everything back around full circle to the thing that we tried to avoid the whole way through, the determinant. I will show you that the classic way you computed the determinant before you took this class is indeed the same way that we're computing the determinant now. That is, the way you built linear algebra from the very beginning, from the ground up, is the same as the way that we did it without the determinant. So first off, we need a couple of definitions, a couple quick things. This will be a relatively short lecture, but it'll be fun. So the sign, or actually before we talk about the sign of permutations, I think we should talk about what permutations are in case anyone doesn't know. I'll start by saying a permutation of 1 through n is a list M1 through Mn where each of 1 through n appears exactly once as some mi, if you get what I mean. That is, it's just some reordering of the numbers 1 through n. Yeah? The set of all permutations of 1 through n is denoted Sn. And I guess I should put these in brackets just because it's a list. Okay, so permutations. Just take a list, reorder it. All right, easy enough. Here's the concept that we'll need related to permutations. The idea is that we'll track how many things got out of order. So the sign of a permutation M1 through Mn in Sn is the quantity minus 1 to the t, where t is the number of pairs jk with 1 less than or equal to j less than or equal to k less than or equal to n, such that j appears before, or sorry, not before, after k in M1 through Mn. That is, basically what we're doing is we're saying, hey, look, you've got the numbers 1 through n in some order. They could be all mixed up. All right, let's look at pairs jk, where j is less than or equal to k, and they both lie between 1 and n. We'll count the number of them where j appears after k in the list M1 through Mn. Notice j is before k in the regular ordering of 1 through n. And so we're checking the number of times that something is out of order, right? The number of pairs of things in this list that are out of order. So, example. Let's do a quick example. And here, you know what? While I'm at it, let me just box these whole suckers up. just to make these notes look super clean. All right. Bam. Okay, so example. Okay, so let's do, say, 2, 1, 3, 4 in S4 has sign -1 since only 2, 1 is out of order. That is, if you look at this, okay, should 2 come before 1? No, 2 comes after 1. Okay, so those two are out of order. But 3 comes after 1, and 3 comes after 2, and 4 comes after 1, and 4 comes after 2. So those guys are in the right order. And 4 comes after 3, so that's in the right order. The only thing that got out of order was these first two. All right, so it's sign -1. That is -1 to the 1. Okay. Similarly, let's do 2, 3, all the way up through, say, n, and then a 1. This guy in Sn has sign. What will it be? Well, let's see. Does 1 come after 2? No, 1 is smaller than 2. Does 3 come after 2? Or does 3 come before 1? No. 3 is bigger than 1, right? So on. Everything here is in order. 2, 3, 4, 5, 6, all the way up to n, right? All of that's in order. But 1 should be at the very beginning. So I've got n-1 things that come too early. They should be at the end. They should be after 1. So this will have sign -1 to the n-1. Oh, okay, that makes sense. So the idea is basically, hey, you got a bunch of stuff. Some of it's in order, some of it's out of order. How many pairs of things are out of order? That's the sign. All right, so here's the idea. I'm going to make a definition for something that I will call the determinant. But I'll put quotes around it since I'm not sure, since we won't be sure until later on that this is indeed actually the determinant that you're used to. So, suppose A is an n by n matrix. Then the determinant, which I'll put in quotes, det A, is going to be defined to be the sum over m1 through mn in Sn of the sign of m1 through mn. Maybe I should put double parentheses on it, but I'm not gonna. Times a m1 1 dot 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 all the way down through a m n n. Okay, so you're just using the permutation on the first index. Okay, and you're taking the big old product right there. The coefficient is the sign. All right, this is the claim that or it's not even really a claim, it's just definition so far. But the claim that we'll make is that this determinant is the determinant that we talked about last time. That is the product of the eigenvalues according to their multiplicity. So let's give an example really quick. All right. The determinant of, say, A11, A12, A21, A22, a general 2 by 2 matrix, is, well, let's just calculate it out. So what are the permutations? So we'll get M1, M2 in S2. Well, I'll take the sign of M1, M2, and then I'll do A, M1, 1, times A, M2, 2. Yeah? Put commas there to make it really clear what's going on. Okay, so you just compute it out. So I'll get the sign of 1 comma 2, a 1 1, a 2 2 plus the sine of 2 1, a, I'll put commas there again just to be clear, a 2 comma 1, a 1 comma 2. See? All I'm doing is I'm basically, if you want to see it, okay, taking like this thing right here. That pops right there. Then I take this guy right here. That goes right there. Likewise, this guy goes right there. And this guy goes right there. See? Just like the formula says. Okay, not too bad. Now I just have to compute what these signs are. What is the sine of 1, 2? Well, how many things are out of order? 0. So it would be minus 1 to the 0, which is 1. So I would get a 1, 1, a 2, 2. Okay, and then the sine of 2, 1, that has one pair of things out of order, since 2 comes after 1, right? So I get minus 1 to the 1. So I'll just write that as a minus sign. Then I'd have a 2, 1, a 1, 2. Hey, that's the regular old formula for the determinant you saw in your first linear algebra class. At least for 2 by 2 matrix, right? Nothing too crazy. Okay, cool. Let's show that the quote-unquote determinant that we've defined here is indeed the determinant that we know and love from our previous lecture. That is the product of the eigenvalues according to their multiplicity. Okay, so to show that the quote-unquote determinant is the determinant that we've been talking about, let's prove a little lemma. So actually I have to prove 2 lemmas. The first one is relatively straightforward. The second one I will actually do without proof, but I will give a sketch of why it's true, mostly because the actual proof just involves a lot of index chasing that if I write out is no more enlightening than just telling you it works. You kind of have to sit through and plug and chug the index chasing yourself to really believe it, which is, one of those kinds of exercises that is best left to people to do on their own. So suppose A is upper triangular. Then the determinant, quote unquote, of A is equal to A1, 1 through ANN, i.e. the product of the diagonal entries of A. So this is the claim. The claim is that this quote-unquote determinant is the product of the diagonal entries. Here is the proof. All right. It's not hard at all. So here's the idea. The permutation 1 through n in S sub n contributes the term sine of the permutation times a 1 1 through a n n, which is just equal to a 1 1 through, got my dot too low there, dot dot dot, a n n. Okay. That is, it contributes this term to the determinant of A, the quote-unquote determinant, since it's defined as a sum of terms of this, or of terms like this. Okay, now for any other permutation, M1 through Mn in Sn, there is some entry mk such that k is less than mk. That is, the only one that has everything in order is 1 through n. Everything else has something out of order. But the only way to put something out of order is to take something big and make it small, or something small and make it big. It's the same thing ultimately. On some level, you're getting some k, so that k is less than mk. That is, mk is too far ahead. Okay. But amk k equals 0 in this case, since A is upper triangular. So sine m1 through mn, a m1, 1, product all the way down through a mn, n is equal to 0, since amkk is equal to 0. Oh. Therefore, I'll write it out, the quote-unquote determinant of A, which is equal to the sum over m1 through mn in Sn of the sine of m1 through mn times A m1 1 a m n, make that n a little bit lower down, mn n. This thing is just equal to a 1 1 a n n. Right? Since every other permutation other than 1 through n, the permutation that leaves everything in order, has in the product of am1 1 through amn n a term, specifically amkk here, that is equal to 0. So the whole thing is equal to 0 since there's a 0 in that product. Thus, the only term that ends up mattering in this sum is the one that we first calculated, which is what we wanted to show in the first place, right? That the determinant is equal to this. Okay, now what can I do with this? Why would I care? Here is the piece that will make it all come together. Here's the claim. Okay, another lemma, which I will not prove, but will kind of give some reason for why you would think it's true. I'll say the determinant, quote unquote, of AB is equal to the quote unquote determinant of BA for A and B, n by n matrices. Okay, so the claim here is that the determinant does not care, the quote-unquote determinant, does not care about the order of a product. Okay, now why is this true? Well, here's the easy way to think of it. In AB, you're going to get the entries of this matrix by going across the rows of A and down the columns of B, while in BA, you'll go across the rows of B and down the columns of A. Okay, so the terms in AB and the terms in BA, they all contain the same information, right? That is, if you're going across a row in A and down a column in B, you're basically getting the same stuff as if you go across all of the rows of B and down all of the columns of A, right? Like that information is contained in there. So this and this, while they can be totally different matrices, they're all derived from exactly the same information, just mixed up a little bit. But the determinant, quote unquote, is all about the ways you can mix things up, right? The ways you can reorder 1 through n. So naturally, maybe not naturally, but just through some index chasing, which is how I'll say what the proof is. The proof essentially boils down to just write it out and use permutations to reorder everything. So really all it boils down to, but boy, is it a long thing to write. So nothing fancy, nothing terrible. Basically, it just says, hey, just write out actually what's going on in AB. Write out what these entries are. When you write out this big long product with these permutations, what you'll see is that every time you have some product of this form, every term in this sum, you can take each one of these guys and turn them into sums. But then when you use these permutations, you can always find some permutation to turn it into a different permutation of an entry in BA, right? And then you can do this in such a way to turn the determinant of one into the determinant of the other. It's tedious, it's long, it's not very interesting, and it's one of those things that if you don't write it out and actually go through the specific index chasing yourself, it's just gonna sound like gibberish if I just say it, you know? You'll watch me write out a lot of fiddly indices, and if you're not actually going through it yourself, it will basically mean nothing. So if you believe me that this does indeed work, then you will believe the following claim pretty easily. So this little fact right here comes from this. So corollary has two R's. I spelled this wrong. Let's just call it theorem. I can't remember how to spell corollary. I spell corollary all of the time, and I never remember how. Okay, so theorem. How about that? The quote-unquote determinant of the matrix of T with respect to a basis U1 through UN is equal to the quote-unquote determinant of the matrix of T with respect to a basis V1 through Vn. For T here in LV and V1 through Vn, U1 through UN, two bases of V, any two bases in particular. That is, taking the determinant of the matrix of an operator does not depend on the choice of basis you use to get that matrix. How does this work? Well, all you need is the exact same thing that we did for the trace. So, by the change of basis formula, there is an invertible matrix C such that A is equal to C inverse BC, where A is equal to the matrix of T with respect to one of the bases. It doesn't matter which one you pick. You can, flop them all you want. And B is equal to the matrix of T with respect to the other basis. Let's make that V1 through Vn. There we go. So, using the last lemma, the determinant, in quotes, of A is equal to the determinant, in quotes, of C inverse BC, which is equal to the determinant, in quotes, of B C inverse C, which is the determinant, in quotes, of B. Right? Hey, how about that? Nothing too crazy, nothing too wild. Okay, so we can do this as long as you accept that one step that I went through without proof, which is normally bad practice, but it's the last day, right? So, what will this let us do? Well, it'll let us see that this is the same as what we talked about last time. So that's the theorem. And this one has such an easy proof, it will just blow your mind. I mean, maybe not. It's basically the same thing we did for the trace. It says the following, which is that det in quotes is equal to det not in quotes, i.e. the determinant not in quotes of t is equal to the determinant in quotes of the matrix of t. Oh, okay. So here's the proof. Let me box everything up here all nicely. So here's all it is. Use the Jordan normal form along with our lemma regarding upper triangular matrices. That's all. So we know that the Jordan normal form lets us get a block diagonal matrix for T, and on that, and those blocks on the block diagonal, or on the diagonal block matrix, are themselves upper triangular matrices with, on the diagonal, the eigenvalues of T repeated as many times as their multiplicity. Oh, cool. Nice. So that tells us that, well, hey, look, an upper triangular matrix has as its quote-unquote determinant the product of its diagonal entries, but if you take the Jordan normal form of an operator, the product of the diagonal entries, that's just the product of the eigenvalues of the operator according to their multiplicity. And that's what the not in quotes determinant we talked about last time was. Huh. Pretty sweet. Okay. So the determinant you've been exposed to before, this kind of thing right here, this take the product of the diagonals minus the product of the anti-diagonals for the 2x2 case, and then this horrible cofactor expansion thing, which really just boils down to this whole business of doing signs and products like this. This is just exactly the same as what we talked about last time, which is taking the product of the eigenvalues according to the multiplicity. So all of the good properties that you learned before about the determinant are indeed true. They all carry over. It all comes from the fact that we're just taking big old products of eigenvalues according to multiplicity. Sweet. There's something kind of cool here that happens in inner product spaces that I want to touch on before we end today. So let's do it. Okay, last little tiny piece, which I think is sort of fun. Here's the quick, we need two supporting results, and then the final kind of conclusion bit of it. So suppose V is an inner product space, and S, an operator on V, is unitary. Then the absolute value of the determinant of S is equal to 1. That's the claim. So let's check it out. Okay, proof right here. Not too bad. It's actually very easy. So determinant of S in absolute value is equal to the absolute value of the product of the eigenvalues of S repeated according to their multiplicity, which, if you look at it, is just the product of the absolute values of the eigenvalues of S repeated according to the multiplicities, which is just going to be 1, since the eigenvalues of a unitary operator have modulus 1. Where lambda 1 through lambda n here are the eigenvalues of S repeated according to their multiplicity. Okay, cool. So a nice little bit of theorem right there. Here's the next claim. theorem, the next claim says the following. Suppose V is an inner product space and T is in LV. Okay. Then the determinant of T is equal to S1 Sn, the product of S1 through Sn, where S1 through Sn are the singular values of T. Ooh, kind of cool. Okay. Remember the picture for singular values? It was all about saying, hey, let's grab a ball, a sphere, and let's run it through T. What are the axes of the ellipsoid that results from this? What's the length of those axes? The major, minor, semi-minor, so on. All the different little chunks of this ellipsoid. How stretched is it, the sphere, in each direction? Okay, so all we got to do for this is use the singular value decomposition. So the proof goes as follows. By singular value decomposition, there exists orthonormal bases E1 through En and F1 through Fn of V such that TV is equal to S1 V E1 F1 plus ... all the way down through Sn, inner product of V with En, Fn. This is the whole business of singular value decomposition. It says, hey, check it out with respect to some orthonormal bases, or in the case that you have something between a vector space and maybe a vector space of a different dimension with respect to an orthonormal basis, E1 through En, and an orthonormal list, F1 through Fm. In this case here, we're taking these to legitimately be orthonormal bases, both of them. What we're saying is that all you got to do is know inner products, singular values, and what these bases are. Nothing crazy. So here's the idea. Take S in LV so that SEK is equal to FK. This defines S since E1 through En is a basis via the linear map lemma, which we proved way a long time ago. That is, all you got to do to know what a linear map does is know what it does to a basis. Okay, then here's what we get. Okay, check this out. The norm of SV squared is equal to, well, let's just go through it. Nothing crazy. All we got to do is we just have to write S and then apply it to V in terms of what it does. So SEK, well, all I got to do now is just slam it out. So here, I'll write this out really quick. This will be S inner product of V with E1 plus ... all the way down through V inner product with En. You can always do this to write V. This piece right here is just V. You can always do this with respect to an orthonormal basis. One of the first things we proved about orthonormal bases. Okay, now I'm just going to use linearity to pull these coefficients out. And notice that S takes EK to FK. Okay, so this just turns into VE1 F1 plus ... all the way down through VEN Fn squared. But hey, F1 through Fn, that's an orthonormal basis. So what is this norm? It's just the squares of the absolute values of the inner products VE1 through inner product of V with En. Oh, Oh, okay, there's just a whole lot of applications of the Pythagorean theorem. Nothing crazy at all. But hey, it's just the norm of V, isn't it? Right? It doesn't matter if you do this with F1 through Fn or E1 through En, right? It's going to work the same for any orthonormal basis of V. Oh. The norm of SV squared is equal to the norm of V squared. So S is unitary. Moreover, T is equal to S times the square root of T star T. Do you believe this? Maybe. If you don't, I encourage you to think about what goes on when you do this. So, all you have to do to find this, I don't want to take some horribly long diversion right here to show you this, but if you don't believe it, just look at what T does. T takes V to S1, V, E1, F1. S takes V to inner product of V with E1, F1 through ... inner product of V with En, Fn. Right? It's everything except for these singular values, S1 through Sn. But hey, wait a second. The singular values of S1 through Sn, or the singular values of T, S1 through Sn, these are eigenvalues of the square root of T star T. And the corresponding eigenvectors are F1 through Fn. So, hence the claim. If you don't buy it, I encourage you to go through and think about it a little bit. Go back to the section on singular values. I don't want to belabor the point. If you buy this, then we get our result really quickly. Hence, the determinant of T is equal to the determinant of S square root T star T, which is equal to the determinant of S times the determinant of T star T's square root, which is just equal to, well, S is unitary. It's the determinant square root T star T, which is just equal to the product of S1 through Sn, since those are the eigenvalues of T star T repeated according to their multiplicity. Oh, whoa. That is pretty tight. Okay, so here's a consequence of this. Here is why I've even bothered to do this part. I just think that this is fun and it gives you better perspective on why the determinant pops up in other math classes, for example, like in Calc 3. Here is the nice fact. Theorem. Okay, theorem. So, suppose that T is a linear operator on Rn, and omega is some subset of Rn. Then, volume of T omega is equal to the absolute value of the determinant of T times the volume of omega. Now, I should be clear when I say volume here. We have to be, like, I really should add some caveats, but they ultimately would make this seem less intuitive than it is. What I should say is that, like, we have to have some way to measure the volume. What does that mean? It's going to be some kind of an integral thing, so we have to make clear that you have to take a measurable subset and so on. But putting those kinds of caveats aside, just think of regular old subsets that you could measure the volume of, nice things that you're used to. Okay, here is the picture of this. So, the idea is that if you have a ball in Rn, then you'll map it over to some kind of an ellipsoid. Maybe I'm drawing this a little bit weird. Maybe I'm just, let me do this here. Select it, let me rotate it a little bit or something. Yeah, there you go. Okay, nice. So this gets moved on over via t. And you've got your I'll say these lengths are singular values. So here is the ball, and t sends it over. So these lengths here, as we've talked about before, these guys are the singular values. This one previously has length 1. You know, it's like a ball of radius 1. It gets mapped over by t. These new lengths are the singular values. All right, cool. So the determinant of t measures, in some sense, just obviously from this picture, change in volume. Oh, that makes some sense. After all you need to calculate the volume of an ellipsoid is the length of it, the lengths of its axes, right? Okay, but the lengths of the axes just come from the determinant, right? Oh, well, after all, the lengths of the axes are just the singular values, and the determinant is the product of the singular values. So we're taking a product of lengths here. This is pretty reasonable to say, hey, look, the product of these lengths tells us volume. Huh, pretty nice. Another way to see this, if you want to see it slightly differently, is just draw some boxes here. Nothing goes on that is even remotely crazy. It actually makes perfect sense if you draw boxes. Just think about how, you could grab like a box of, maybe I'm going to draw this box here like this. And then I could draw a new box right here. And what is the volume of this box? The area? Well, it's the product of these axis lengths. Oh, that's the product of the singular values. So it says, hey, map the box over. What happens to the box? How does its volume change? It changes according to the product of the singular values, which is the absolute value of the determinant. Huh. Cool. Pretty nice. Pretty neat. So I think that helps explain why, helps you see how the determinant pops back up in places like calculus. Like if you're, transforming something, you're trying to look at like nearby, let's linearize this map. Let's take its Jacobian, right? Then we're going to look at something with the determinant of the Jacobian near that point. It's saying, how do we change volumes near that point? Naturally, the determinant should pop up, since the determinant is measuring how volume changes. Kind of cool. All right, I think that's enough. I think that's enough for today. Let's call it quits, and let's say goodbye. All right, guys. Like I said, it's been fun. It's been a genuine pleasure. Thank you for letting me teach you linear algebra. It's been my honor, and I wish you nothing but the best of luck in all your future endeavors. You are all exceptionally bright and talented students, and if there's ever anything I can do to help you, please just let me know. I am always happy to help with any math class you take or any math question you have. I'm always happy to try to hook you up with internships, connect you to opportunities, or give you advice if you need it, or work on research with you, or just chat math. I'm always around. Drop me an email anytime. It's been fun. Bryce signing off. See you next time, guys.